Okay, you guys, so today's lesson is focusing on something called static equilibrium, which is basically how to keep things from moving. So, like, forces act upon each other to prevent things from staying this, forces act upon each other, which can sometimes, if the forces are exact opposites, can create a sense of static equilibrium, which means that the object doesn't move. Okay, so I kind of made this little thing. This is a magnetic ruler and this is a magnet. So basically the idea is if I have a force and it's pulling this way, then the magnet will move. Okay, if I have a force that's pulling this way, the magnet will move. But if I go like this and I pull equally from both things, that because these forces balance each other out, the magnet won't move. Okay, so force one, force two, if they're equal, then this object stays in the same spot. Okay, it's kind of the same as gravity. So this magnet right here would obviously fall to the ground, but the force of me holding it equals the force of gravity keeping it still, keeping it in its place. Okay, so sorry I don't have more examples to show you, but that's kind of what I came up with. So we are going to do some kind of straightforward problems with static equilibrium. There is a worksheet for this, so if you don't have a printer, it's no big deal. Just get graph paper out. If you have a printer, then go ahead and print this. Okay. All right, let me get a little closer. Hold on. Okay. Sorry. I know that's going to make things easy there. Okay, let's see. Can we see all of that? Yeah, we can. Okay. All right. So the first one kind of started off a little straightforward. There, like each time it jumps, it has one more vector. So this one, if you have a vector pulling, so this is like the object you want to keep still. If you have an object pulling this way, then to keep it still, you just simply pull the exact opposite direction. So you're going to go, instead of west to north 3, you're going to go east to south 3. Okay, so exactly opposite will keep that vector in the same spot. Okay, so why doesn't that look right? Okay, well, so when you write it, you would write vector 1 is negative 2i plus 3j. Okay, and vector 2 is positive 2i minus 3j. You know you did it right is when you add those and you get 0 i's and 0 j's. This is what makes it static. Okay, all right, so obviously it's a little harder if you have two. We do know that if this one is, they're both pulling east, so our result vector is definitely going to pull west, and it looks like it's pulling more north than south, so my guess is that the result would pull it more to the south and more to the west. Okay, but you don't want to just guess, right? So the best way to do it if there's more than one is to write the components first. So this is 2i plus 5j, okay, this one. And vector 2, which is this one, sorry, the label turned out a little weird, is 2i minus 2j. Okay, we need vector 3 to be a vector that makes this all add up to 0. So this is 4, so if you put a negative 4 there, it adds up to 0. This is 3, so if you put a negative 3 there, it adds up to 0. So this vector is going to be 1, 2, 3, 4, 1, 2, 3. So this vector right here, okay, makes it static equilibrium. Okay, all right. So basically the same thing for the third one. Is just an extra practice problem. So F1 is 1i plus 2j's. Okay, vector 2 is negative 2i plus 5j's. Okay, vector 3 is negative 5i minus 3j's. Okay, and then again you want these to add up to 0. Okay, so this is negative 7 plus 1 is negative 6, so this is going to be positive 6 that it adds up to 0. This is 7 minus 3, which is 4, so this is going to be minus 4, so that it adds up to 0. Okay, and then I do want you guys to draw that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, and it should make sense. I mean, if they all pulled the same direction, then you would know that something kind of weird happened. Okay, all right, so, and I know you can't see, here, let me move it a little bit. There we go. You can't see all of that one, but I think you got the point. Okay, so there's one word problem we're going to do with this. Okay. I think I'm like a little close or something. Hold on. So you can see the whole problem there. That's better. Okay. Okay. So this says two forces act on an object. The object you always want to just assume it's at the origin because it'll be easier. One force has a magnitude of 30 units, okay, and acts on the object at an angle of 45 degrees. And it does define what a unit is down here in case you haven't taken physics yet. So 30 newtons and 45 degrees. So 45 degrees is right there, okay, and this is 30 long, and that's the magnitude, okay. All right, and then another force has a magnitude of 70 and it's an angle of 120, so that's right here. Okay, and that one is 70. You know what I'm gonna do is, I can't really make my 71 longer, but this one's way shorter, so sorry, I'm gonna make this one way shorter. This one should be like less than half the length of the other one. Okay, all right. So what we wanna do is we wanna find this one we're going to call F1. This one we're going to call F2. We're going to find a third vector, F3, that balances these both out. So this is pulling both to the north. So our vector is definitely going to pull to the south. And this is pulling more to the west than this one. So my guess is that our vector would be down here. Okay. All right, so this is the first step. It says find force F3 that would create stack equilibrium. The first thing you have to do is do what you did on the previous problems, is you have to find F1 and F2 first. So you are going to use that formula that we've been using a lot. You're going to use this. Okay. And lucky for you, I did give you the direction, so you don't really have to work very hard at this. Force 1, I gave you that it was 30 was the magnitude. And I gave you that the direction was 45, okay? So these are both unit circle ones. You can work in exact answers if you want, but it will make it a little harder because these have like root 2's in them. The other one will have root 3's in them, and then they're kind of hard to add together. So even though this is on the unit circle, I'm gonna go ahead and just use my calculator and type this in. So 30 cosine 45 is 21.213. And then I don't have to type this one in because I know it's the same, because sine 45 and cosine 45 are the same. Okay, so that's my force 1. Okay, and then force 2 was a lot longer. It was 70, and the angle was 120. Okay, and then again, I'm just going to go ahead and type this into my calculator, and I'm going to get negative 35, and that's exact because the cosine 120, of course, is negative a half. And then this one is 60.622J. Alrighty, so in order to find F3, we have to know what F1 plus F2 are. Okay, so you're going to take the I components of F1, add them to the I components of F2. Okay. And when you do that, you get negative 13.787I. And then you're going to add the J components together, the 21 and the 60, and you're going to get 81.835. Okay, and don't forget, it's really easy to forget this part. We don't want F1 plus F2, we want F3. And remember, F3 has to balance these both out. Okay, you have to get 0 and 0. Okay, so F3 is going to be positive I component, negative J component. Okay, so this is my vector F3. Okay, and let's go ahead and just sketch a graph of that, even though it's going to be kind of hard to do perfect. But negative 13 is not very long. Negative 81 is pretty long. So this vector is going to be here. Okay, F3, which does make sense to me. So, you know, if you get it to the wrong quadrant or something looks funky, just go back and check your work real fast. Okay, all right, and then part B said find the force, which is just the magnitude. Okay, actually just says find the magnitude, but it does mean force. Okay, so magnitude, of course, is just Pythagorean theorem, 13.787 squared plus negative 81.835 squared. Okay, type that into your calculator. Okay, and you get that this one is 82.988 newtons. Okay, All right, so that's how much force is pulling down to keep this item stable, okay? And then to find the direction, okay, I need to know, remember direction is from here all the way around to here, okay? So what you're gonna do is you're gonna do a triangle, just like we did at the other kind of bird wind problems, okay? And this right here is the angle that you could find, okay? We know that this little orange line right there, okay, is the 13.787, and that orange line is the negative 81.835, okay? So we can use tangent of negative 81.835 over 13.787. Okay, so do inverse tangent in your calculator. Okay, and that will find us just this angle right here, which my calculator says negative 80.437. Okay, actually that actually is the answer because it's in the right quadrant, but we never use negative numbers for direction. So to get the positive value of that, just add 360. So the direction is 279.563, which makes sense because we know that 270 is right there. So it's just a little bit past that. Okay, so the video is a little shorter this time because I did put some conic review on the back, and I want to make sure you guys have time for that. So if you don't remember how to do a parabola, hyperbola, or ellipse, go ahead and look at your notes, or you can come to my office hours. All right, bye.